Stop worrying about homework and start learning with confidence. This is Asklan. Complete help for every subject. Like, share, subscribe for daily learning videos.
In this problem, we have a particle entering a region of space with a uniform magnetic field, and it's traveling perpendicular to that field. When that happens, of course, the particle will travel along a circular path. In this case, it only travels 1/4 of a circle, heading east, then turning around and heading due south. So let's just get a quick visualization of what that looks like. So we would have a region of space here with a magnetic field, in this case, pointing outward. And then we'd have a particle heading with velocity v, say to the right. In this case, this would be due east, and then down here would be due south. Now, when the particle enters this region of space with this uniform magnetic field, what happens is it follows a circular path. In this case, we'll only go 1/4 of the path and then head, to turn to color of black, right, for a particle, and then it's going to head due south this way. So, we're asked several questions about this situation, and we're given several pieces of information. We know the mass of our particle, we know the speed of our particle, we know how long it spends in this region, we know the delta t here, and we also know the magnitude of the magnetic field through which it is traveling. Now, this is one of those problems where it's actually easier to solve for part B first and then solve for part A. So that's what we're going to do first. Part B here is asking us to find out the magnitude of the charge of this particle. Now, remember, we know how to relate the motion of our particle to characteristics of the particle through our equation for the radius of the path as a particle moves perpendicularly through a uniform magnetic field. That means if we want to find the charge of that particle, we just solve for that by rearranging our equation a little bit. Oops, little mistake there. That is now going to be our radius down here. So we have this expression here. Now, what do we not know? Well, we don't know the radius here. So we don't know the radius of this path, but we know some information about the velocity, and we know some information about the time. So we can figure out how to relate those things together. So let's think about the motion that this particle is undergoing in this problem. So it's going to travel a 1/4 circle of a path here, and we'll say that distance that it travels is a distance d. So we know from physics 1 how all these things relate to each other. We know that the velocity of the particle is going to be the distance the particle travels divided by how long that it took to travel. But we know that this particle, the distance it's traveling, is only 1/4 of the circumference of the circle. A circumference of a circle is 2 pi r. Divide that by 4, and then divide that by delta t. So we ultimately see that the velocity of our particle is given by pi times r divided by 2 delta t. Now, we don't know what r is, so we can solve for it and plug it into our equation here. So solve for this here, and then once we solve for it, we can plug it into here. So solving for our r real quick, we get value of 2 times the delta t, how long it's in that region of space, multiplied by the velocity, all divided by pi. So we're going to take this expression here, plug it into here, and then we're going to be able to get our answer. So what is the charge of this particle? What's the magnitude of the charge of the particle? It's going to be given by m, it's not an m times v divided by 2 delta t times v times b, all divided by pi. And that comes from plugging the expression for the 2 delta t v over pi expression in for r. Now, when I do some simplification, I see the velocity goes away, and I get that we have m times pi divided by 2 delta t times the magnitude of the magnetic field. It's actually going to give us the value of the charge of our particle. So we plug everything we know into here. We have the mass of our particle, which is given as 7.2 times 10 to the negative 8 kilograms. Pi is pi. We'll little calculator carry that out to as many decimals as we can. And then we have a time that it's in this region of space, 2.2 times 10 to the negative 3 seconds, and the magnitude of the magnetic field through which it is traveling is 0.31 teslas. Plug all that into our calculator, and we see that the charge of our particle is 1.7 times 10 to the negative 4 coulombs. So that is the answer to actually part B of this question. Now that we know the value of this charge, which in order to finish this problem, let me just clear this off real quick. Now that we know the value of this charge, we can then just use it to solve part A pretty quickly. So part A asks, what is the magnitude of the magnetic force that is acting on this particle? Well, we know the charge is 1.7 times 10 to the negative 4 coulombs, and we know that the equation for the magnitude of the magnetic force acting on a particle is the charge of that particle multiplied by its speed, multiplied by the magnitude of the field it's traveling through, multiplied by the sign of the angle between the magnetic field and the velocity. We know that this is going to be a sine of 90 because the magnetic field is perpendicular, and this term is going to go to 1. So all we need to do is plug in the charge of our particle, 1.7 times 10 to the negative 4 coulombs, multiply that by our velocity, 85 meters per second, and then multiply that by the value of the magnetic field through which the charged particle is traveling, 0.31 teslas. So in the end, we end up getting that the magnitude of the force acting on this charged particle in order to cause this particular type of motion is equal to 4.4 times 10 to the negative 3 newtons. And that is the answer to part A of our problem.